So let's start with the webinar. Today's topic is our THB, the Transient Hot Bridge, the instrument for determining thermal conductivity. For those who do not know Linseis, a short introduction of our company. So Linseis Messgeräte was founded in 1956 by Dr. Maximilian Linseis, who you can see here on this picture. And it was founded here in Selb in Bavaria and Germany. We manufacture here also all of the instruments, have an all sales and also service locations in the US, China, and India, and more than 65 distributors worldwide. So we are producing here measuring instruments for the thermal analysis, for thermal conductivity, and thermal electrics. We also have some of our instruments within our lab and offer some measurements here. The company now is owned by the son of Dr. Maximilian Linseis, Klaus Linseis, and his two sons, Florian and Vincent Linseis, are also part of the company right now and are leading the production and the sales. Here is our product range. So we have some calorimeters, some TGAs, also SDAs in our product range, as well as some classical dialectometers, also instruments for thermomechanical analysis, some instruments for the thermal conductivity determination, for thermoelectric materials classification, as well as two instruments for the characterization of thin films in the nanometer or micrometer range, and also, for example, an instrument for the Hall effect analysis. What makes us unique is that we offer a lot of different options and customizations. So, for example, for EGA, high pressure instruments, measurement under hydrogen, and so on. So we offer a broad range of different temperature ranges, so different furnace options, and also are open to some customizations and some projects which are unique. On this slide, you see the agenda of today's webinar. So first of all, we will have a look on how to generally measure the thermal conductivity. Then I will give an overview over the THB itself and its sensors. Then I will explain how the sensors work, how the measurement works, and then I will go into detail on how to perform measurements. So first of all, how the sample can be prepared. Because of that, I will also give a short overview over the accessories we offer for the THB. And then we will have a look onto the software and in some application examples. In the end, there will be a summary of what I have shown in this webinar. For the measurement of thermal conductivity, there are in general two methods, the transient methods and the stationary methods. The transient methods, here the sample is subjected by a thermal disturbance, and this disturbance is observed as a function of time. So there will be a heat input into the sample, and the transient method already start to observe the reaction of the sample when this disturbance is brought in. So in this part here, the stationary methods or steady-state methods wait until there's a stable temperature gradient through the sample. So when the heat input is the same as the heat flux which comes out of the sample. So this will be then here, this part of this curve here. So the transient methods already start measuring when there is a disturbance within the sample, and the most important techniques which belong to the transient methods are the hot strip, hot wire, hot plane methods, or also the THB, as well as the well-known laser flash method. The advantage of these methods is that they measure really fast, so they have a short measurement time just because they're already measuring when the thermal disturbance is brought in. They can measure a very broad thermal conductivity range as well as a broad temperature range. But the problem with the transient methods is that the theory is typically more complex, so that the evaluation is a little bit more complex. And for the laser flash, only the thermal diffusivity is determined and not directly the thermal conductivity. But this is a disadvantage of the laser flash and not of the transient method in general. The stationary methods, due to the needed waiting time until there is a steady state, take a longer measurement time, but the advantage is that the results will be then very accurate and they can be evaluated rather easily. What is a little bit problematic with the stationary methods is that they're typically only for lower conductive materials, so there's a limited thermal conductivity range and also a limited temperature range because it is not so easy to observe the heat flux within a high temperature environment. As already mentioned, the transient hot bridge belongs to the transient methods. Yes, so we will measure within that thermal disturbance in a material. Our product range for thermal conductivity instruments is rather broad. So we have the classical laser flash instrument and the THB for the transient methods, as well as the TF-LFA, the LFA for thin films, belongs also to the transient methods. The second thin film analysis instrument, the thin film analyzer, shortly TFA, measures also according to a transient measurement method using a hot wire principle for the thermal conductivity determination. The heat flow meter and the TIM tester we offer belong to the steady state methods and are using a plate method where you have two plates which apply the temperature gradient to the sample. These both two are for lower conductive materials, the heat flow meter, especially for building and insulation materials, whereas the laser flash and the THB are for a broad thermal conductivity range. This is also illustrated here on this slide, where you can see the thermal conductivity range here on the bottom. And here the different instruments. You see that the THB has a more or less the broadest thermal conductivity range. The laser flash system has some difficulties for the very low thermal conductivities, but the THB is more limited in the temperature range. Because of that, the laser flash is still the most universal instrument. But with the THB also, a lot of different applications can be realized. The THB was developed within a cooperation between the German Meteorological Institute, PTB, and our company, Linseis, and the first instrument was launched in 2011. And since then, we worked a lot on the THB. And starting from 2021, we have a new version of the THB, which was optimized in electronics and in software. Our transient hot bridge instrument is available in 3 different models. THB Basic, THB Advanced, and THB Ultimate. The difference between all of them is the thermal conductivity range. So the basic model can measure up to 5 watt per meter Kelvin, so especially suited for the polymer range and the building industry range. The THB Advanced can go up to 500 watt per meter Kelvin, so covering also a lot of different metals. And the THB Ultimate has the broadest thermal conductivity range and can go even up to 1,800 watt per meter Kelvin. The THB allows fast and easy measurements of the thermal conductivity and thermal diffusivity of materials, and by knowing the density, also the specific heat capacity can be determined. The THB allows the measurement also of solids, liquids, powders, and pastes, so it covers a very broad range of applications. The temperature range goes from minus 150 degrees Celsius to 700 degrees Celsius, so also covers a lot of different applications. We have a lot of different sensors available for the THB. These can be classified into two groups. So we have Kapton foil sensors, which are shown here, and we have sensors based on a ceramic substrate. These are for the high temperature applications. The Kapton foil sensors can measure maximum up to 200 degrees Celsius under air, and this range can be extended with an inert gas atmosphere up to 300. The different sensors which we offer are all for different applications. So the classic THB sensors are for solids. Enhanced with a metal frame, they can be easily used for liquids, pastes, and powders. The QSS sensor, I would tell a little bit more in a few slides later, is for the high conductive samples, and the hot point sensor, due to the small tip here, which is the sensor more or less, is very good suited for very small samples. More or less all of these Kapton foil-based sensors are also available with the ceramic substrate. So the THB sensor, the QSS sensor, and the hot point sensor is even realized within two options for the high temperature measurements, one for the solids and one for the liquids. So all of these sensors have a different application. The good thing is that the THB is a plug and play system. So you can just switch off one sensor and connect the other one immediately afterwards. The software automatically recognizes the type of sensor. Here you can see a short overview for what type of application the sensors are useful. So as mentioned, the basic laminated versions are for solids, especially with a metal frame, for liquids, pastes, and powders. We have two different THB sensors. One is a little bit smaller and the other one is a little bit larger, for different thermal conductivity ranges and also for different sized materials. And the QSS sensor, especially for samples with a high conductivity, and the hot point sensors, especially for very small samples. So the THB sensor is a patented sensor and is suitable for fast and high accuracy measurements, and can determine the thermal conductivity, diffusivity, and specific heat capacity of solids, liquids, powders, and pastes. For each application, there is an own sensor. The QSS sensor. QSS stands for quasi-steady-state and is suited for samples with a high thermal conductivity, and the sensor has a special layout and uses more or less both, so a transient and also a steady state method. It combines the advantages of both methods to be able to determine high conductive samples in a easy way, so without a complex theory. Yes, so as mentioned, it's for the high conductive samples. Because of the different layout, it is able to go to higher thermal conductivities compared to the THB sensor. So here also the measurement times are slightly higher compared to the THB sensor for the same thermal conductivity range, as it needs to wait until there's a quasi-steady state. The hot point sensor, as mentioned, is for small samples and also very good useful for anisotropic samples, because it only has here the small tip as a sensor, and because of that, one just needs a 3 × 3 mm squared sample to be able to perform some measurements. Also, the sensor is useful for solids, liquids, pastes, and powders. And with the ceramic versions, one can go up to 700 degrees Celsius. The hot point sensor has the highest uncertainty of all of the sensors because of the simpler sensor layout, and it is only able to determine the thermal conductivity. The THB and the QSS sensors can only also determine the thermal diffusivity, and because of that, also the specific heat capacity. But how do these sensors work? The sensor serves as a dual heat source and a resistance thermometer. So within the Kapton foil, there is some wires embedded, which will heat the sample using a heating current, and due to that, the sensor is also heated itself, and the recognized temperature rise over time is then a measure for the thermal properties. So what one does is one embeds the sensor within 2 sample pieces. So here you see the illustration. This is more or less the sensor, or simplified, it is a hot wire. And there is the thermocouple, and during the measurement, the sample and the sensor will be heated, and one will get a temperature increase with time. Based on that, one is then able to determine the thermal conductivity. The THB is an enhancement of the just shown hot strip or hot wire technique. So the start of the thermal conductivity determination was the hot wire, and due to some different layouts, so we have here such a meander shape, and this is separated and connected to a Wheatstone bridge. Because of that, there are some advantages. So one has a higher electrical resistance, one compensates end effects, and one has an enhanced sensitivity because of this modified layout. The temperature increase, which one needs for the evaluation for the thermal conductivity, is directly connected to the bridge voltage, and because of that, one is then able to find out the thermal conductivity of the material. Also, what is very advantageous for the THB instrument is that the sample preparation is rather simple, as well as also the software. So for the measurement, one needs 2 pieces of the material. They need to have the same size as the sensor foil so that the complete sensor foil is covered. And the surface needs to be smooth. And then if one has the sample ready, one just sandwiches the sensor in between those 2 sample pieces so that the sensor foil is completely surrounded by the material. And then one presses the configuration a little bit together. This is done to enhance the thermal contact and reduce the thermal contact resistance between the sensor and the sample. Additionally, one avoids some air in between the 2 samples. So the sample setup is very easy. Sandwich the sensor and the samples, press it together, and that's all. Also for liquids, powders, and pastes, this sample preparation is very easy. Typically, it is enough to just use a beaker, fill it up with the liquid or powder, and hang in the sensor with the metal frame here, which is not visible within the water. Here is also the metal frame tip. The metal frame is necessary for the liquid, powders, and paste measurements because the sensor foil is very flexible, and with the metal frame, it is more stable. And within a liquid, it is then avoided that there is a bending and the heat generated by the sensor will be accumulated. So with the metal frame, it's very stable and because of that, then useful for the measurement of liquids. To realize different applications, there's, of course, a broad range of accessories. So on the one hand, there are different furnaces available for different temperature ranges. So here in the pictures, you can see our Peltier cooled furnace, which can measure from -20 to +50 degrees Celsius. So especially suited for polymers. Here you have then a sample holder, where you just put in the or prepare the sensor sample sandwich, and then here on the top, there's the possibility to put some weight on top so that the configuration is also pressed together. For a well-defined pressure onto the sample, there's also a contact pressure control available so that one can measure also thermal conductivity independence on the contact pressure. There are also different sample holders, one for liquids and one for powders. For powders, there's a special designed sample holder available where you fill in the powder, put in the sensor, and one can then also compress the powder for the measurement. What is new available is our single-sided sensor. Here, one side of the sensor is insulated, so by that one has a more or less directed heat flow to the specimen. And the advantage of the single-sided sensor is that one just needs one sample piece, and because of that, it is a non-destructive measurements because typically one has a piece of material and then needs to cut it into 2 parts to be able to sandwich a sensor. Here, this is not necessary. And yes, because of that, also just half of the sample surface requirements are necessary. And additionally, it is also often not so easy to prepare the surfaces so that they fit very smoothly on top of each other. To avoid some air gaps in between with this single-sided sensors, this is avoided. It is also very easy to use. Also the same level as the other sensors. And because of the insulation on the one side of the sensor, the measurement of high conductive samples, so especially metals, is slightly improved. As typical, if there are some advantages, there are also some disadvantages or drawbacks. Here, the problem is with the single-sided sensor. The lower conductive materials are not easy to measure. One has a lower measurement range and a lower accuracy, because the difference between the insulation material and the sample is not that strong, and by that the accuracy is lowered. Additionally, the determination of the thermal diffusivity does not work as well as with the two-sample setup, because one has just the insulation materials on the one side. Also, the thermal conductivity determination has a slightly lower accuracy compared to the two-sample setup. So, yes, as already mentioned, the sample preparation is very easy with the THB. Also, the THB software is very easy to use and is not crowded with a lot of information. So one has the possibility to store some measurements. So one sees which sensors already is connected. As mentioned, it is a plug-and-play system. You can disconnect one sensor and connect immediately afterwards another type of sensor to the instrument. One can give some information about the sample. One sees the graphs recorded during the measurement, so the bridge voltage and also the temperature increase, which are necessary for the thermal conductivity determination. And one can see the results within a table immediately after the measurement. So depending on the type of the sensor, the recorded measurement curve looks a little bit different. So for the THB sensor, you can see an example here. So we record the bridge voltage and also the temperature increase. And from the bridge voltage, we need to take the derivative for the THB sensor to be able to determine thermal conductivity. For the thermal conductivity, here the maximum is relevant, and for the thermal diffusivity, here the decrease. So the shape should be similar to this black curve. For the QSS sensor, as it is a quasi-steady-state sensor, we need more or less a saturation, and this can be seen here in this bridge voltage. We see here an increase, and then afterwards, more or less a stabilization. This can be also seen very good here in the bridge voltage, where the derivative goes back to zero, or more or less to zero after it reaches a steady state. After the measurements, one is also able to export a report with the measurement data and also with the measurement curve. This will look then similar to this one. So one can export it as a Word document or also as a text document. On the next slide, I have prepared a recording of the software. Hopefully it works. I just need to find out how to start. Now, okay. So here you see the software, a THB sensor is connected and a PMMA sample is measured. The used heating current is also determined automatically. So first, a short test is performed to find out the optimum heating current, and also the measurement time is determined automatically. Here you see the measurement running. Now we have reached the maximum of the derivative of the bridge voltage, and the derivative is now decaying to be able to determine the thermal diffusivity. And as soon as the measurement is finished, the table here on the top is updated, and we see the result of thermal conductivity. And yes, so it's very easy to use. One just prepares the sample and more or less just needs to click on start here, because the heating current and also the measurement time is determined automatically. Within the next slides, I have prepared some application examples. So here on this slide, you can see the measurement of 2 hydrated salts. The measurement was performed from -20 to +30 degrees Celsius, and a THB metal sensor was used. So a small metal framed THB sensor. The sample was filled in a beaker, and the beaker was put into a tempered liquid bath to be able to set the different temperatures. The sensor, as can be seen here, was just hung into this, the material, and then the measurement was performed. Within the results of the thermal conductivity independence on the temperature, one can see that the different phases of this phase change materials can be directly seen also in the thermal conductivity results. At room temperature, going down to 10 degrees Celsius, the material was more or less liquid, and shortly below 0, it started to be solid. And this can be clearly seen here in the thermal conductivity results. Within this slide, also an application example is shown where some soft compressible insulation materials were investigated under different levels of compression. Here, not the pressure was determined, but the sample thickness was controlled using such a manual press. And then the sample thickness was measured. Here also a THB sensor was used, but without the metal frame. And one can clearly see here that the thermal conductivity changes with the sample thickness. So it's also relevant for soft materials to know exactly the measurement conditions to be able to understand the application and the results of the thermal conductivity more in detail. So in summary, I have introduced to you the THB, the Transient Hot Bridge instrument. It is an accurate measurement, transient measurement method of the thermal conductivity. Advantages is that it is an automatic measurement, so a one-button solution. Just connect the sensor and press on start, as the heating current and also the measurement time will be determined automatically. This means that no experienced staff is necessary to operate the instrument, and one cannot influence the measurement too strongly by using wrong measurement parameters. Advantages is also that the thermal conductivity and the thermal diffusivity can be determined, and because of that, one can also calculate then the specific heat capacity. The measurement is very fast. you have seen in the example of PMMA with a thermal conductivity of around 0.2 watt per meter Kelvin, it took like 20 to 30 seconds, one measurement, so it's very fast. And by using this single-sided sample sensor, one does not need to destroy the sample by cutting it into two halves. The instrument is very small and light, so it's a small tabletop instrument, which you can also carry around in a suitcase. A small disadvantage of the THB is that it's not an absolute measurement method, so it needs to be calibrated with a certified material, but the calibration is also not complex. One more or less just performs a classic measurement to be able to calibrate the instrument. We also offer a broad range of calibration materials. So now I'm at the end of the presentation. So I presented to you our Transient Hot Bridge instrument, showed to you the different sensors which are available and the different accessories, showed to you some examples of measurements and also how the samples need to be prepared, and also demonstrated shortly the measurement software. So please feel free to type in your questions into the chat. I will go through it one after the other. One question was regarding the single-sided sensor, how much the accuracy is lowered of thermal conductivity determination. I'm opening the slide of the QSS sensor, as the single-sided sensor uses also the QSS sensor design. Here the uncertainty is, depending on the thermal conductivity which one investigates, is between 5 to 10%. And for the single-sided sensor, it's maybe starting from, let's say, 7% and goes up to 12%, so maybe 2% lower accuracy. A further question which was asked is why one needs a furnace if we have a wire inside the sensor. The wires within the sensor heat the sample only locally, so they increase the temperature of the sample by a few Kelvin, typically between 1 to 4 Kelvin, so that the power of the sensor is not enough to be able to control the sample temperature. It brings only a small disturbance into the material. Because of that, it's necessary to have an external furnace to be able to perform temperature-dependent measurements, so that the sample and also the sensor are at the target temperature, and then the sensor is able to heat up the sample locally by a few Kelvin for the evaluation of thermal conductivity. Regarding the samples, there was also a question, what is the minimum thickness of the sample? So the thickness of the sample depends also on the used sensor. So there's a rough guide for polymer samples. Typically, one uses the THB sensors. Here, the minimum thickness should be maybe around 3 millimeter to make sure that the generated heat by the sensor also stays within the sample, so that the surrounding material or atmosphere does not influence the measurement. Here, the minimum thickness is typically 3 millimeter with the THB sensors. For higher conductive materials, the minimum sample thickness is a little bit higher, so 5 millimeter. And for the high conductive samples, which are typically measured by the QSS sensor, one should have at least 10 millimeter thickness. The same requirements also apply to the single-sided sensor. So a minimum thickness of 3 millimeter for lower conductive samples should be offered, and for the higher conductive samples, maybe 10 millimeter. In general, the sample should cover more or less the complete sample surface. So the complete sensor foil, the sensors have a size of 20 × 40 up to 40 × 80 millimeter. The QSS sensor is about 25 × 55 millimeter. So for the THB, rather large samples are needed. Regarding the maximum sample size, one is more or less completely open. There are just some minimum requirements for the sample sizes for the THB measurements. Also, there was a question regarding the degradation of the sensors, so how many times the sensor can be used. So the sensors are very durable, so one can use them for a very long time, but this depends also on the application. So for high temperature applications, the lifetime, of course, shortens. So the THB sensors, as already mentioned, can measure up to 200 degrees Celsius. If one constantly performs measurements up to this limit temperature, the lifetime is shorter compared to just some measurements at room temperature. And also the lifetime is shorter for measurements under high contact pressures or for samples with a rougher sample surface. So it depends a little bit on the application, but typically one can use the sensors for half a year to a few years even. So they are very durable. Our next question, which came up, is how deep does the sensor heat the sample? So the sensor contains some heating wires within the THB sensor. This is more or less here, this region. For the QSS sensor here, you can see in the middle the heater and the resistances on the outside, which measure then the temperature increase with time. And these heating and measurement wires more or less heat up the sample to some millimeters. This is why the sample thickness should be higher compared to the penetration depth. Within the software, one can also have a look onto the penetration depth. So in the software, you can also select here thermal penetration. Then it will also calculate an estimation on how deep the heat generated by the sensor was penetrated into the material. For lower conductive materials, this is typically between 2 to 3 millimeter, and the higher conductive the material, the higher will be also the penetration depth. But mostly it stays within a few millimeters. The next question which came up is what portion of the hot point sensor should be covered by the sample? I have mentioned that the hot point sensor is especially suited for small samples. So only 3 times 3 millimeter squared samples are necessary. The thickness here should be also at least 3 millimeters or higher, depending on the thermal conductivity. Here on the tip are the measuring wires. So here it's a little bit more closer. For the ceramic version, so only this portion should be covered. Here only the front part, the same for the laminated version, and the same also for the ceramic version for the liquids. Here you have a microscope image of the tip. Here and here you see the heating wires, which will measure the thermal conductivity. So it is necessary only to cover here the front tip. As within the other sensors, the wires are completely distributed over the sensor foil. Here, the requirement is that the sensor foil is more or less completely covered. A further question is which sensor is recommended for construction steels? This can be easily answered. This is the QSS sensor. The THB sensors can measure only up to about 5 watt per meter Kelvin, and the QSS sensor is especially suited for the higher conductive samples. The hot point sensor is more useful for very low sample amount, and it's morely used for comparative measures. Further questions concerns the roughness of the sample surface. As mentioned before, to be able to have a very good sensor sample sandwich, one needs to press the configuration together. And a very rough sample surface can then damage the sensor foil. So there are no strict or defined requirements regarding the sample surface. One just needs to, if one touches the sample, it should not be too scratchy, too rough, so that the sensor foil can be damaged. Here one can use as well a trick. So one can apply a very thin layer of thermal paste or a copper paste on top of the sample surface so that it's smoothened, and then one can bring in the sensor. And of course, with a rougher sample surface, it's better to use a lower contact pressure to compress the configuration. So these were now the questions which arise during the presentation. Are there some further questions? So yes, if there are any further questions coming up, you can also contact us. Here, the email address is mentioned. So if there are any questions regarding THB, you can come back to us, write us an email. If you have interest also in some measurements with the THB, you can also contact us. Yes, so at this point, I want to thank you very much for your attention, and hopefully I could bring to you the THB and demonstrate that it's a very useful tool for the thermoconductivity determination for a broad range of materials. So thank you again very much for your attention.